All right, so today's video is going to be, I'm going to get that pointing more towards that. More derivatives. So we're actually going to start to get to some shortcuts today, which is phenomenal. So just going to kind of sum up some stuff we've been doing, adding a little more in. So look at this graph right here. The first example, let's label the points where the slope of the graph is 0, or is it positive, or is it negative? So let's start at 0. So if the slope is 0, that's a tangent line, straight line, perfectly horizontal. So that means that we're going to reach either a top or a bottom. Okay, so look at my graph right here. At B, I'm going to draw a horizontal, my best horizontal line across B. Same thing with E. So B and E are 0. Positive is going to be anything. I'm going to look in the video to make sure that it's backwards for me. So positive is going to look like that. It's going to be increasing. So which ones are increasing? Looks like I got C and D. Negative, which ones are there you go. Which ones are decreasing? Well, that's going to be A and F. All right. Now let's get a little more into these. And again, in the corner, a little helpful formulas here. The definition of the derivative, and then the difference quotient, or the alternate form. Let f be a function that satisfies this right here for all real numbers. We're going to go ahead and find f prime of 2. Okay. So given this information, which one of these formulas do you think would be easier to use? So I'm given f of 2 plus h. Probably the top one right there. Okay, but instead of x, I'm replacing it with the number 2. So I'm going to do the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. So just replacing the x's with 2's, and then I'm good to go here. So now I'm just going to just replace everything. So x approaches 0 is going to be 5h minus 3h squared plus 9h cubed all over h. And what's really nice about this is that I have a GCF of h through all of these, so I can actually take out an h. I'm going to purple this one up. I have h, and I'm left with 5 minus 3h plus 9h squared. That's purple right there is the factored form of the numerator right there. So what's going to end up happening is those h's go away. So you're going to get the limit of h approaches 0 of 5 minus 3h plus 9h squared. Now I'm capable of plugging my 0 in, and I'm going to left with just a 5. All right. Some more understanding of these two formulas and what we can do with them. What information do they give us? So we're given this right here. We're given the difference quotient. So at 5, we get 3. So what this is saying is that the derivative of f at 5 is 3. The derivative for part A at 5 is 3. That must be true. It's gotta be true. The derivative at 5 is 0. Well, you can't have the same derivative at 2 different points, so that's never true. I forgot to see. The value at 5 is 3. I don't know enough information here, so this might be true. F is continuous at 0. don't know. I really don't. We don't know anything about 0, so this is a might. This is good stuff now. We're getting to the good stuff. F is continuous at 5. What do you think? Yeah, really? I'm going to agree with you. That must happen. If the derivative exists, it has to be continuous. Because if it wasn't continuous, there would be no derivative at that point. So that must be true. And let's do part F right here. The limit as you approach 5 equals f of 5. This is actually like the definition of continuity. So this is a must. This is step 3 when you're finding continuity. Got to show that. So if it's continuous, then step 3 has to be true. Okay. Oh, we're so close to me showing you a shortcut. We're so close. All right. This is on the screen. No, let me zoom out of it. I don't think I zoomed out at all. No, I didn't. I'm good. Okay. Let f be a function that satisfies this property. So again, f of x plus y equals f of x minus 4 f of y plus 9xy. For all real numbers, suppose that the limit of f of h over h is 2. Find f prime of x. This can get a little tricky. So we're going to see this y right here? What if I made this y into an h? Right, if I plugged in an f of h for it. This would kind of sort of look like my definition of derivative. So I can say that f of x plus h is indeed f of x minus 4 f of h plus 9xh, because you are free to plug in points. So it's just really translating this into this. All right. So we can just go ahead and use that definition of derivative. We could do other fancy things if we really wanted to. But real quick, I can make this look like the entire numerator. So here is, so this is what I have. This is what I want, is right here. I want f of x plus h minus f of x. Now you could just go ahead and just plug this in and you're totally fine. Okay. I'm going to go just a step further. I'm going to do some magical math. What if I were to move this f of x over? So f of x plus h minus f of x equals negative 4 f of h plus 9xh. Just trying to get you to think about math on a little bit different level here, okay? Instead of just directly plugging in, I kind of killed the step right there by just moving that over right there. Oh my gosh, it's so awesome. If you're not comfortable with that, that's okay. It's not the end of the world. I'm just trying to get you to think outside the box a little bit with math, because that's what we need to do. So we know that the limit as h approaches 0 of x h minus f of x over h. I'm just writing that down so that I can now just pretty much substitute everything in that I do know. So I'm going to get negative 4 f of h plus 9 x h all over h. All right, so we have those limit properties that I said are super important. Yeah, let's go ahead and use them, because I can't plug in a 0 because I don't know what f of 0 is. So, but I do know this, that the limit as x approaches 0 of negative 4 f of h over h, and hey look, I'm going to start to get somewhere, plus the limit as h approaches 0, 9xh all over h. And stuff's going to start to happen here. So first off, that negative 4, if you feel more comfortable, you can put that in front. It's just a constant. But f of h over h, as we're doing the limit as h approaches 0 gives me a 2. So this is going to give me a -4 times 2 plus, don't these h's go away? So I'm left with just a 9x. So I get -8 plus 9x. And that it would be f prime of x. Okay? All right. Finally here, the moment I've been waiting for, where I can start to teach you a little bit of a shortcut. Okay? Something that I like to call, or everyone likes to call, the power rule. All right? What it is if I have f of x is equal to x to the a, the derivative, that's supposed to be an a and not a 9, the derivative is going to be a x to the a minus 1. What I mean by that is if I have an x to the third, okay, the derivative is going to be multiply that power in front, so it'd be 3, x to the, just take away 1 from the power. Super easy way to find the derivative. Let's rock on. So knowing that information, instead of going through this example right here, because it wants us to find the derivative, it's telling us to use a shortcut. So I'm going to show you how. Instead of actually going through and cubing this and simplifying it, let's just find what the function is. Do the derivative. Okay. So for this first one, the function that I'm given here, you have to know which one you're given. I'm given the definition of a derivative, which again, bring it all back here in this little corner right here. F of x is what's being subtracted. So what's being subtracted in this first one? 2x cubed. Prime for the power rule, you just take that 3, multiply out in front, which gives me a 6, subtract 1, 6x squared. That's it. With this one, a little bit trickier now, okay? Because now they're giving us numbers, not just x's. So we kind of have to figure out what's happening here. Well, again, this kind of sort of looks like this right here, okay? And they clearly plugged in a number to make this match that. What number do they plug in for x? They plugged in a 9 because it's 9 plus h minus f of 9. So it says to find f of x and a. So a is equal to 9 for us. That's what they plugged in, okay? The function, now replace the 9 with an x. The function, replace the 9 with an x, is going to be root x. Which you're saying to yourself, how do I use the power rule? Well, that's the same thing as x to the 1/2, isn't it? Here we go. So the derivative of this, f prime of x, is going to be, multiply that on the front, which is 1/2, x to the 1/2 minus 1, negative 1/2. If I want to write this a little bit nicer, I would just put that negative 1/2 on the bottom. Even nicer, looks like this, okay? That's the derivative. Now let's find the derivative at 9, because that's what we're actually trying to find, is the derivative. Sorry if that wasn't on the screen. The derivative at 9. I'm just going to plug in a 9 now. So I'm going to get 1 over 2 root 9, which is 1/6. Which I believe is a problem that we did from old notes. 1/6. All right. This one. This looks like a difference quotient. Very obvious that a is going to be 2. Okay, difference quotients are super nice because the a is super obvious because it's always going to be x minus something, right? So it's 2. The function, also easy. It's in the beginning. So the function is going to be 3x squared plus 2x. Okay, so I'm going to take the derivative of that guy, plug it in 2. So the derivative of x is, I'm going to take the derivative of each term individually. So I'm going to do 3 times 2, which is 6. Take away 1. X to the 1. Just write down an x. Plus, there's an imaginary 1. So 1 times 2 is 2. Take away the 1. So 1 minus 1 is 0. X to the 0 is 0. So I'm going to get just a, no, sorry, x to the is a 1. X to the 0 is a 1. All right, so that's why I just get a 2. All right, derivative of 2x is 2. First off, it's a line, right? 2x is a line with a slope of 2. You could have done that from algebra 1. So the derivative of 2x is also 2. One thing with that way. All right. Now let's plug in my a value. Better than that right there. Bothering me. Plug in a 2, and I'm going to get 12 plus 2, which is 14. And that's going to wrap up our section on more derivatives. Finally getting to the power rule, but still using that to make those difference quotients, definition of derivative, much easier on us.